Let me start by thanking the organizers for invitation to present my work here. So I'm going to talk about the same problem that Rami just talked about, but I guess my approach is a little more conservative, since it's going to be in the context of sort of exploring this in the context of semi-classical geometry. And I think it's pretty clear that my main conclusion is going to be inconsistent with his. So I guess you're going to have to make up your mind which one you want to go with. But it is true that I am not really going to try to describe the quantum state of the black hole. So maybe you could say that we should have reversed the order of the talks, and that he would have told you how to take a more modern view than the sort of backward look that I'm going to be giving you. Anyway, this is based on some recent work with David Lowe at Brown University, and then in turn it also sort of draws on some much earlier work going all the way back to the early 90s. So let me just remind you what the problem is. And so as originally formulated by Hawking, we should imagine the following process. We have some diffuse matter that's described in a pure quantum state, and this is very much in the background of some geometry. We're not really trying to describe the quantum state of the matter, so this is just some matter that's in a quantum state. So the assumption is that we can use some effective field theory to describe the combined system of matter and gravity. This undergoes gravitational collapse, it forms a black hole, and then the black hole, if it's a large one, it sits around for a while, but it gradually emits radiation. And then at the end of the day, you have, if you assume that the black hole completely evaporates, you only have outgoing thermal radiation. And in the semi-classical approximation that Hawking used and that Rami described in the previous talk, this is thermal radiation. So the whole process as a whole has started with us in a pure quantum state, and it has evolved into a mixed state, which cannot happen if in the usual framework of quantum field theory. Okay. Now, since I have this tendency to go long in my talks, I've learned the hard way that if I want to get to the end, it's best by starting with the end. So this is my final slide. It's the summary. And so what the conclusions that I want to leave you with is that this problem, in fact, cannot be analyzed by using only local effective field theory. I think we would agree with Rami there. But I think what we do disagree on is, it comes in here at the end, is that you can, in fact, I would claim, use field theory suitably defined to describe the experience of an observer who falls into a very large black hole, where that it basically, until they get close to the singularity, and certainly much later than the square root of m length scale that Rami was introducing, so they will not run into any problems until then. So that's the main conclusion. There are some steps on the way. Basically, one can, of course, react to this paradox that Hawking discussed. You can react to it in different ways, and I'll mention a few of them. I'll not go into them. But string theory, and in particular the ADS-CFT correspondence, suggests rather strongly that there is some unitary dual description. And so this has led a lot of people to, and I think Rami also mentioned this, sort of to take the view that by the time, eventually when we sort out this problem, we will conclude that there is a unitary evolution, and we have to then understand what is it that has to give. And in these recent work on firewalls, it's really a rather strong a violation of the equivalence principle once you hit the horizon. I guess that's also what you would say in Rami's description. Okay, so it's not a Planck length inside; it'll be more like a Fermi for a okay. Well. Okay, so you would simply say that once you get inside a black hole, the equivalence principle doesn't apply anymore, because you don't have a. Well, that's maybe splitting hairs. So let's just see where I get to with this. So what I will do is work on the assumption that the problem is unitary. I will explore in terms of this what you might call a phenomenological description, because it's certainly not something that we can derive in any solid way, although I will give you some arguments just based on quantum field theory in black hole background for this view, that you have this picture that although you have asymptotic observers can in principle recover the information from the black hole, an infalling observer who is passing into a large black hole shouldn't run into any problems until the curvature gets strong. And that's of course assuming that you can use a classical or semi-classical geometry also on the inside of the black hole, so that's very much different from what we were told in the previous talk. All right, so let's just remind you of some very elementary things about black holes. So I'll be focusing on just simple Schwarzschild black holes in this talk. And remind you that there is, at the horizon, the curvature is in fact rather small if the black hole is large. So in fact, in the limit of a very large black hole, the horizon is a basically flat space-time. And so that has led Hawking and others to the expectation that physics near the horizon should in fact be very classical. And so let's keep that in mind. Now here's the Penrose diagram for the black hole formed in gravitational collapse. I think that's quite familiar. The important thing is, of course, that this surface here, this event horizon, is a surface of very large redshift. So there's an infinite redshift from if you emit a photon from here, that just barely makes it out to infinity. And so that's going to lead to a lot of the is of course at the root of a lot of the confusion and the disagreements in this subject. And now I'm not going to go into the calculation. We saw it in the previous talk, but basically the end conclusion of Hawking's calculation is that if you assume a vacuum state at early times before the black hole forms, and then you evolve your operators in that state, you conclude that there's an outgoing flux at future infinity, which is that of a black body at a certain temperature that goes inverse with the mass of the black hole. And of course these are very much formal issues, because if you put in some numbers, you'll find that the black hole lifetime that you would estimate from this goes like the mass cubed, and if you have a solar mass black hole, it's 10 to the 71 seconds, which is much larger than. So these are not something that we have to worry about for astronomical black holes, but of course this is a problem that we want to think about, learn something about gravity and the nature of gravity in general. So that's not. Okay, so my Penrose diagram that I want to look at is slightly different from what Rami had, but I think it's. So here's basically a black hole. This part is the same as before, but now we're going to have the evaporation, and I'm assuming that the black hole completely evaporates so that we get back to Minkowski space later on. And possibly if there's some small remnant left behind, that would just, this r equal to 0 would just be the word line then of that remnant. Okay, now I think something which is maybe not always said, but is certainly at the back of mind of all discussions of people when they discuss these problems, is that you're going to be using effective field theory. Now, if you look at the actual calculation that Hawking presented in his original paper with using the geometric optics approximation when tracing back the rays, so he was, of course, in this one here. So basically, he used the fact that when you trace back the rays here, you have a very high blue shift. It comes back here, so high that you can ignore whatever the stuff here is that is made here. And so at intermediate stages in the calculation, he's using trans-Planckian and very much way beyond Planckian energies. And so this, of course, is something that you might worry about, whether this is something that you should be concerned about. And but what you can convince yourself of, and we'll see an example of it, or I'll allude to an example of it later on, is that this is not really going to be, not necessarily a problem. You should be able to formulate your evolution on a set of Cauchy surfaces, which start out being, in the early time here. You then, as long as these surfaces avoid regions of strong curvature, which means in this problem the deep black hole interior, and of course also this region here when the black hole has become small, is about to finish evaporating, then of course it's also a high curvature object. But if you should be able, until your evolution runs up against either the region here or deep inside the black hole, the expectation is that one should be able to use a local effective field theory, which is basically classical gravity theory with some corrections that should be under control perturbatively. Now, and you can in fact construct a set of slices that does this. It was first outlined by Bob Wald in '93, and then we had a more explicit version of it in our paper. So this is a set of slices which sort of you can evolve forward, and you can capture much. You cannot capture all the radiation going out, but you can capture out a significant fraction of this of the total radiation that comes out from the black hole. Can be on a time slice going out simultaneously with the same time slice is showing is actually intersecting the infalling matter before it actually goes into the black hole. And you can in fact set up this a paradox already on a time slice well before you actually run into the neighborhood of this strong curvature region. And what is nice about this, at least until you run into these problems, is that it's a funny slice, of course. It's a very stretched slice. This Hamiltonian is going to look kind of funny there. And in particular, it's going to be time dependent. If you have a time that that labels the slices as you evolve forward, your Hamiltonian is going to be slowly time dependent, because we're assuming that this is a large black hole and that there are no large curvatures or. And in fact, you can also, I didn't say so, but you can in fact make sure that these slices are such that they are also not only do they avoid strong curvature in the spacetime, but they also are not strongly extrinsically curved. So they're not, they're sort of gently bending rather than. But in this evolution then, when you have a time-dependent Hamiltonian, you expect there to be particle production, and this would be how Hawking emission comes about in this picture. Now, this is, of course, not a very convenient way to actually calculate the Hawking spectrum, but it's in principle you should be able to do it. And what's important here is that you would be seeing low energy emission in an effective field theory that doesn't really run into any strong curvatures. So you would therefore expect Hawking's answer, even though he used trans-Planckian energies at intermediate stages, to actually hold. And of course there are many different ways of doing the computation. Most of them will involve high energies at some intermediate point, but they all agree on the end result. Okay, so let's see if we can, so why doesn't this simply just work? And so this works fine as long as you don't try to insist, so long as you don't insist on unitarity. Because in this description, and of course this was Hawking's conclusion, when you evolve forward on slices like this, part of your state will go inside the black hole. That's not accessible to outside observers, so you would have to trace over those degrees of freedom, and that's what leads to the initial pure state, leading to a mixed state on the very late time slices when the black hole is gone. So we can see that how you run into problems if you try to both have your cake and eat it. So we imagine a Gedanken experiment, which has been analyzed in many versions over the years. So you imagine you have a singlet pair, call one member of them 1, the other 2, and 1 is sent into the black hole along with an observer who traditionally is called Alice in these stories. Alice is instructed once she gets inside the black hole to measure the spin along a z-axis and transmit the result immediately outwards. Now, of course, she's already inside the black hole, so the message is not going to come out. So what Bob, who sits out here, he hovers outside the black hole at a safe distance for a while. He makes observations on the Hawking radiation, and if the information about everything that goes in eventually comes out, this is really a unitary process, he should in principle be able to measure what the spin, what is the outcome of the measurement of Alice's in there. Okay, so in a sense, this Bob observer here can also measure this spin here. And now, of course, this is where we are violating the usual rules of quantum mechanics in that we're having 2 space-like separated observers making a measurement of the same spin, so 2 independent measurements of the same spin. Now, meanwhile, Charlie goes even further away from the black hole and can in fact be, by the time you conduct the experiment, can be practically arbitrarily far away. And then just to see how we might get into a problem here, Charlie was instructed to throw a coin when he gets out here, and then depending on the outcome of the coin toss, either measure along the z-axis or the x-axis. Okay? Now, if he measures along the x-axis, then of course we know by the usual EPR that whatever result he gets out here, Alice will have gotten the opposite. On the other hand, if he measures it's the z-axis. If he measures the x-axis, then those are not correlated, and therefore Alice can measure either one. Okay, and now Bob. Same thing goes, of course, for Bob's measurement. Measurement of if they measure the same component of the spin, Charlie and Bob, then they will have to disagree, and then if they measure different components, they're not correlated. Now Bob does the measurement, drops into the black hole, receives the message from Alice, compares the 2, and there's a finite probability here that Bob will realize that his measurement disagrees with that of Alice, and then he will have learned that Charlie actually measured the z-axis and not, the x-axis and not the z-axis. And what that, and of course you would have to do this with some, not just a single spin, but single pair, but with some ensemble and do some statistics. But basically, what this cloning of the information in the radiation is achieving here, it's taking the EPR correlation, which normally cannot be converted into any sort of communication across space-like separations, and is actually turning it into an EPR communication about what happens out here, seen by this observer here. Okay. but what ultimately, in a different language that will put us make contact with recent work on these firewalls. Of course, what we started with here was a maximally entangled pair here, and then through a measurement made out here, we're transferring the entanglement to be between state out here and on the inside, and that is basically what we're trying to do here is to have this mode here. It starts out being entangled with a spin over here. If the entanglement is then transferred to between here and here, then this guy cannot be entangled with this anymore, and you will basically run into a firewall problem that way. We'll come back to that in a minute. Okay? So there seems to be something going wrong here. We cannot, and you see, this can all be carried out before this nice slice here is getting close to the singularity. So it's not that we are sort of, effective field theory seems to be breaking down here if we assume that the information goes out. Of course, what maybe you might say is a more natural assumption is that the information doesn't go out. Effective field theory is fine, and you just run into a problem that you lose information by the time the black hole has evaporated. That, of course, was the conclusion that Hawking drew from all of this. But now we're going to step away from that and say that, well, we're going to insist that the information comes out, and then there must be something going wrong with this effective field theory. But it's happening without usually an effective field theory warns you that it's going to break down because some curvature gets strong or some extrinsic curvature somehow, and that's not happening here. Okay, so as I mentioned, Hawking basically said this is something that we have to take at face value, that once you include gravitational effects, you're going to lose information from the world. You have to basically reformulate quantum theory so that you can accommodate non-unitary evolution. And this has been followed up by Unruh and Wald in more recently, and it's something that Hawking, of course, proposed a theory. He made a serious attempt to generalize quantum mechanics. Now, that particular theory didn't work very nicely, sort of modulo some technical assumption. You could show, and it was shown that his model was, which basically was the evolution of density matrices rather than states, and allowed density matrices to evolve from pure to mixed. It was shown by Banks and collaborators that you could actually rewrite that model as a conventional quantum evolution coupled to a random source at the Planck scale. And so you might say that his theory sort of fails phenomenologically, because that then you will not get a ground state that looks like empty space-time. You would get some basically Planck temperature state out of it. So another possibility is, of course, that the information doesn't go away. It simply gets left behind in a remnant. That also runs into phenomenological problems, at least the naive version of it, because you will need a different remnant for every possible initial state of the black hole. Now, the semi-classical approximation that Hawking used should be valid down to close to the Planck scale. And so you would have basically an infinite number of different remnants at Planck with around the Planck mass, so that's an infinite spike in the density of states, and that runs into problems when you think about pair production of these and how they would couple to just ordinary. Since everything couples gravitationally, you would run into problems trying to make sense of that, although there are some ideas in the 90s that have been also developed a little bit further, which sort of made considered remnants in higher dimensional theories, which I've sometimes referred to as TARDIS remnants. They're sort of small on the outside and large on the inside, and those geometries could accommodate a lot of information, and it wouldn't be very accessible because it would be in the specific examples that Banks and O'Loughlin were studying, there was a long throat in the geometry, and the information could be far down that throat, which would make the remnant couple very weakly to ordinary matter. The version that I will focus on is, of course, that the information is returned in the Hawking radiation. In particular, this picture put forward in the 90s by our group at Stanford and simultaneously by Kim and the Verlinde brothers. And there are some other work that has been sort of in the same direction. Now, of course, there's the fuzzballs, and I guess following previous talk, we need to add a line here, which is these quantum states that Rami was discussing. And furthermore, there's this notion of the firewall, where the black hole eventually develops a hard shell, so that you, if you fall into it, you run into basically you get projected into a unique state, and that resolves the problem because it means that no information can go into the black hole, and therefore you don't lose any information beyond that. Okay. Yep. I'm not going to try to explain it, since I don't I don't think that proposal is right. So you'll have to get somebody else to defend that. But I think you're right that there are issues there that it sort of starts with a semi-classical picture, and then at some stage departs from it rather radically. That's right. Yeah. Okay. Well, but on the other hand, the whole point of the paper was to say that that picture was inconsistent. So, okay. Well, let's not worry about it, because well, yeah, clock is ticking. As I said, you basically have to get somebody else to defend that one. But all right, let me just very briefly mention this input from string theory that we've had over the years. That doesn't really address this problem directly, but it has certainly influenced how people think about it. And sort of, if you allow me to talk with it, it has influenced people's beliefs. So one is, of course, that at least for a certain subset of black holes, these near extremal supersymmetric black holes, we can actually count the number of microstates and understand the microphysical basis for the entropy. And basically, if you do that, there isn't any large number of microstates. And string theory doesn't have the density of states at the Planck scale that you would need for remnants. So it basically, people lost interest in them, I think partly for that reason. Partly for the models that people were exploring, these higher dimensional remnants were kind of baroque and complicated. That, I think, was another reason. And then there is the gauge theory gravity correspondence, which tells us that it should be unitary. And again, it's not easy to formulate the problem directly there, because the black holes where you have an information problem are what you would call small black holes in ADS-CFT. You have black holes that you can form, and then they will evaporate. the very large black holes that are easy to describe in the ADS black holes that are much larger than the ADS scale, they don't evaporate. And so it's very hard to formulate. They're basically stable objects. They correspond to thermal equilibrium states in the dual field theory. And so, and the small black holes are things which are actually not, they're not nice in any way. They're not simple operators. They're not single trace or even multi-trace operators in the dual field theory. But you can nevertheless take it sort of as a as telling us that there must be some underlying Hamiltonian evolution, or in the dual system, that's going to provide you with a relation between an initial state and a final state, even though you can't describe the intermediate state nicely in the gauge theory. And sort of following that, David Lowe and I, we tried to ask what, since this unitary evolution will inevitably involve some non-local effects, we tried to give some estimates of how large are these effects. And if you had a black hole which was, even though it was small on the ADS scale, was still macroscopic, what we found in the ADS context was that these, and I believe Rami said as much in the previous talk, these go like e to the minus the entropy of the black hole. That is e to the minus n squared, which means they're non-perturbative in the 1 over n squared expansion. So no amount of 1 over n corrections to when you're constructing bulk states in ADS CFT, no perturbative construction is going to get you to the point where you can resolve this problem there. So that's, of course, is a frustration. Okay. So let's go back to black hole complementarity. And so basically what we did back in '93 was to say, basically follow Tuft and Page earlier, and simply say, okay, we're going to insist on unitarity, given, first of all, because these attempts to have non-unitary evolution, and also because of the remnant issues, don't seem to be working very well. So let's just see, what do we have to give up if we insist on unitarity? And so we postulated 3 properties of the system. First one is simply that there is an S matrix, so that is the assumption of unitarity. The second one was that if you're not near a black hole or trying to go inside it, physics should be described as usual by some effective field theory. And so we insisted that outside the black hole, and in particular outside what we call the stretched horizon of a black hole. Now massive just means large here, but I used the word from our paper. And exactly where this stretched horizon is well, it is at least 1 Planck length, 1 Planck unit outside the event horizon of the black hole. But in fact, if you're using an effective field theory, a natural place to put it is basically a length that is of order the cutoff scale in your effective field theory. So that could be a TeV if you're, or 100 TeV. So that's what we mean by, and it's very important that this effective field theory, or these semi-classical field equations, only hold outside the stretched horizon. In order to describe the full system, you have to supply some dynamical description of what's going on at the stretched horizon. And we did not back then have any good proposal for that, and that's to some extent still the case, that we don't really have a good description of the stretched horizon dynamics. But it's absolutely crucial that the effective field theory that you can apply only holds up to the black hole. You're not allowed to take it inside the black hole. If you do, you will run into, and this we observed already back in that paper in '93, you will run into contradictions with the assumption made here in number 1. Okay, and then the number 3 was simply that the black hole carries an entropy which is equal to the Bekenstein-Hawking entropy. No, just saying that if you happen to be working in an effective field theory that where you're only interested in phenomena, then you would put your stretched horizon there. In fact, in astrophysics, where they do, where this came from, I mean, this notion of a stretched horizon wasn't original to us. It was Kip Thorne and collaborators and for them, you know, the stretched horizon was placed basically closer to the black hole than whatever scale that they, you know, if they were discussing a binary, they put the stretched horizon, you know, it was, you would want it to be closer than that, but it was actually rather unimportant exactly where they put it. So, you know, if you had an accretion disk, it was the same thing. And our claim was simply that this sort of macroscopic stretched horizon that the astrophysicists found convenient to use should be viewed as some coarse graining of some underlying quantum stretched horizon that you would put at whatever is the cutoff of your theory. Okay. Now, then we had, not as a postulate, although it's sometimes listed that way in recent times, called postulate 4, was what we said is that there is a common belief which we share, which is that an infalling observer who's falling into a very large black hole shouldn't, because the curvature is as small as you like, it just goes inversely as a power of the black hole mass, you shouldn't really notice going, and then whether you and that is a statement basically of the equivalence principle. Now, this of course, as we just saw earlier, is a violation. This means that you have to somehow have the information about the infalling matter in two places. It's both gone into the black hole with the observer, but in some sense, but at the same time, it's also being emitted out in the Hawking radiation, and this is not something that one can normally do. So that is definitely an issue that you have to face up to. But the claim that we made shortly following that in some follow-up papers is that actually if you're this violation can actually not be seen by any low-energy observer. That is, every time that you try to find out that this duplication has taken place, you can only establish that operationally by involving some Planck scale physics or trans-Planckian physics. And so we would claim, therefore, that this is consistent with known low-energy physics, but it certainly implies non-locality, and in fact non-locality over rather, over arbitrary length scales for a very large black hole. If you think about a very important local event in our lives, that is, when it ends, this principle says that if you fall into a black hole, there's disagreement as to where this event takes place, right? You would think it happens somewhere deep inside the black hole when you run into strong curvature. Your friends who are watching with alarm that you're falling in would say that you got destroyed at the stretched horizon. Now those can be very widely separated. Okay. So let's go back to this Gedanken experiment and see how we avoid this conclusion. And what we find is that, of course, that Bob has to wait some time before he comes out, before he can actually read or conduct his measurement. And if you have a young black hole, then Page arrived at the conclusion that you have to wait for half of the photons, Hawking photons, to come out before you can see anything. I think Rami would tell us that you don't have to wait quite that long, but you still have to wait parametrically long time before you get anything. And if you have an old black hole that's been sitting around longer than this so-called Page time, which is when half the entropy has been emitted, then Hayden and Preskild showed, using some techniques from quantum information theory, that any further, if you had actually been following the history of the black hole, you had been conducting experiments. Basically, you surround the black hole with a Dyson sphere and you do all sorts of correlation experiments, and you know what is the state of the black hole, then any further information that gets thrown in starts coming out quite soon. It actually comes out in this thing which is called the Scrambling Time, which for a Schwarzschild black hole in 4 dimensions is of order m log m. That's going to be a recurring time in the remaining 5 minutes that we have here. Okay, and so what you find then is that this guy has to wait at least this scrambling time before he can go in, and then you can do the geometry and you'll find that this guy can actually not send the message without using a Planck scale. They would have to carry out the experiment within a Planck time before, because if they wait any longer, then their future light cone is not going to intersect the world line of this observer who comes in later. So this experiment can't be carried out in practice. But you can learn something from it though, which is that if this guy who's out here does a measurement, remember that actually projects the state of the spin that we took in. Now more generally, the Hawking radiation as it emerges from the black hole goes out, it spreads out, becomes very diffuse, and it basically decoheres into some definite configuration, which effectively will also project the state of the infalling stuff. And in fact, when enough Hawking radiation has come out, it has become the larger of the two subsystems. If you think about the original pure system, pure state, there's a subsystem which is what's left in the black hole, and there's another subsystem which is the outgoing radiation. And by the time that the Hawking radiation is the bigger of the two subsystems, contains more degrees of freedom, then it, in fact, this decoherence will project the state of the infalling matter into a specific state, and that is, of course, exactly what is this thing you call a firewall. And so we made this observation in 2006 that, in fact, that any observation of the Hawking radiation, or even just its decoherence as it falls out, will burn up the infalling observer at the horizon. Now, of course, we weren't clever enough to call it a firewall. We just said this can't be the case and moved on to try to think about the non-local effects that would avoid it. But then this was made, rather clearly in these papers. This point was made rather strongly, and this is basically called the Firewall Paradox nowadays, which I think is a bit unfair to Hawking, since it's really the arguments that go into it are exactly the same ones that in the calculation exactly the same that he did much earlier. No, I mean we simply said that it would project the state of the observer, and that basically means and we had in mind that presumably it would be some sort of stretched horizon picture that would do that. Now let me, in the very few minutes that we have left, just very briefly, so I was going to mainly actually talk about this, but it's just like I told you, I very seldom get to the end of this talk. So at least you've seen the final slide already. But you can actually make some, more than just this hand waving that I gave you about this black hole complementarity. So basically by reanalyzing some, just a scalar field theory, take a conformally coupled scalar. This is work done in the 70s, and in 1980 was sort of the culmination. And you can ask, what is the renormalized stress tensor near the horizon of the black hole? And this is, of course, a well researched subject. And the conclusion was that you will get, if you pick your vacuum right, if you pick the Unruh vacuum or the Hartle-Hawking vacuum, then you will find that there is a finite stress tensor. But actually, mode by mode, the energy, if you ask about what is the energy density for an infalling observer, it is actually mode by mode, it would blow up. It's easy to see. But it's only when you add up the contribution from all the modes and you put in the appropriately tuned counter term that you get a finite answer. But this should have you worried, because a pure state is not going to be the Unruh vacuum. There are going to be fluctuations away from it. It's going to look an awful lot like the Unruh vacuum, but it's not going to be exactly that. And therefore, there are going to be modes that are fluctuating out of that state. And then why are you going to run into a problem there? And we conclude that yes, in fact, the fluctuations over time that when you have some pure state that's evolving will in fact lead to divergent stress tensor at the horizon. So why doesn't that then affect an infalling observer is a question. And so there were some details here. But the reason is the following, which is that if you have a large complex system which is in a pure state, it's going to look, to the casual observer, if you only make observations, only look at correlation functions that are, involve a small number of operators, it's going to look, for all intents and purposes, like a thermal state. In fact, you can be quantitative about it, and Seth Lloyd was in his thesis. You can see that a typical pure state, this is basically an average over the Haar measure that's being used here, gives you an answer for typical observables, expectation values of typical observables. By typical, you mean you have to be a bit careful. They cannot be symmetries. Not allowed to commute with a Hamiltonian. So sort of a thing that I have in mind is take the air in this room, and I calculate the density-density correlation between these 2 points here. It's going to look like it's air at, that it's a thermal system at some temperature plus some very small corrections. And the corrections go like an inverse power of the dimension of the Hilbert space, which in our case is e to the minus s. And so our infalling observer, as long as it's a typical infalling observer who doesn't know about the details of the quantum state, that observer is going to see the thermal result because whatever they do see, this might, if this divergence here would get cut off by some characteristic cutoff in your effective theory, you're going to get this suppression factor here. Now, it's the Bekenstein-Hawking entropy of the black hole. So it's a very large number. Yeah, absolutely. Yeah. So this we would claim is therefore an infalling observer doesn't see this. Now, the next thing I was going to then do for you is to tell you how you actually model the black hole interior. I think that was the inside view, right? So we didn't get to that. Oh well, that's a. If anybody's interested, I'm around for another day, so we can talk about it. But there is some. If you allow me for 1 minute, I'll give you. Yeah. So we have a construction, which basically involves patching up. And I guess there are 2 points I want to make. One is, once you have this outside theory, which is unitary, you could say that's enough. I mean, we just know you form a black hole. And it's only if you insist on being able to describe the experience of somebody falling in that you run into problems. Well, that means we've now said that we're only going to try to see that there's no drama for something you call a typical low energy observer. So you need to construct an effective theory that sort of follows that guy as he goes in. And you can do that. And so we made a construction. But it only has to work, this theory, on a restricted set of time slices. It has to work because as long as the observer is still far away from the black hole, you can use this, what you might call the exact description. And it's only when you get to the stretched horizon a lot further that you need to supplement that with something else. And it turns out that you can do a construction where the observer enters here. These are a set of time slices that have convenient properties. You can use them to follow into the black hole. They're not the nice slices that I talked about because they really do run up against the. And you find that if you make a construction where you inherit the state from the exact description out here, you simply very crudely patch it onto Hartle-Hawking state in here. That is, by the argument of Almeri et al. And others, is going to lead to a firewall. But we chose to take this a scrambling time earlier than we needed, because then by the geometry of the black hole, you can show that that firewall will actually run into the singularity before you actually come in. So it cannot affect anything with our observer. And then we cannot use this description beyond another scrambling time because I would start seeing inconsistency with the exact description when you have further Hawking radiation going out. That's the time scale by Hayden and Preskill. But that's also okay because by that time, this observer will necessarily have hit the singularity. So you can actually get this effective description. And this was just a geometric sort of, it was a suggestive construction that we had in a paper last year. And then this year, what we did in a very recent paper that came out last week, or maybe 2 weeks ago, we adopted this lattice model, infolding lattice model of Corley and Jacobson, and where we can explicitly do computations. You can see that correlation functions get suppressed when you try to compare notes between observers that come in at a later time, and so on. So you can be a little bit more concrete, but so we skip over that, and we're back at our summary.
Thank you very much. So we have time for one question. Okay, so. Okay, good.
In your picture, if you have a system that will do neutron star,
Yes.
particular mass m, and another observer who is looking at a black hole of mass m,
Yep.
how does it distinguish between the quantum states?
Well, the neutron star has cooled down. It would not be emitting any radiation. It's a stable object. Okay. Uh-huh. Mm-hmm. Okay. Yeah. Yes. Yes.
Now I start with a neutron star and a dynamically collapsing and forming black hole, and I run into trouble.
Do you? Because I thought I think Rami told us that what you will form is a black hole, which is a very specific one, which is practically pure. Yeah. Yes. Uh-huh. No. Well, I would suspect that the Hilbert space has all these states beforehand, and that it only that. No, certainly in this picture. I thought you wanted an answer in. No. This picture doesn't address it. Absolutely not. That's true. This is just a semi-classical. Yeah. This is a semi-classical picture which precisely doesn't address this. That's sure. No. Yeah. No, I was trying to follow you there. And I would think in quantum gravity you have these states already, and that your system is then only going to explore a small fraction of this Hilbert space. At least that's one way it could work.
Okay, good. Since we are 25 minutes late, it's better to end here. We will resume at 11:10.